Hi there everyone, Oliver H here. I thought I'd just try recording one of these workshops just so you guys can watch through it at your leisure. And I thought I'd start with the one on probability because this is sort of quite an important one to know, and it's going to be the sort of thing that turns up in our assignments and exams. And I thought as I did this I might try to work through it at the same time with half an eye on the assignment, because of course we get questions in our assignment like this asking us to calculate a variety of different probabilities and not telling us what sort of probabilities they are. So we need to just double check we can correctly identify those probabilities, how we should answer them, and make sure we can do that. So the example we've been given is this example on COVID-19 testing. And of course there's two parts to it. One is the initial test that people were given. Did they initially test negative or test positive? And then later those people were then retested with a more thorough test and confirmed to either have the virus or not have the virus. And then we'd like to be able to calculate our three different types of probabilities that we need to know on those: joint probabilities, marginal probabilities, and conditional probabilities. And so it's important that we can read a question, say in an exam or assignment, and identify from the way that question's worded which of these three probabilities are they asking about. And then finally, the other thing we'd also like to be able to do is ultimately do a independence test, a chi-square test, to work out if those two things are independent. Alright, now often, so in this case we've been given the full table of counts, which is what we need to calculate our probabilities, but that's not always given to us in an exam or assignment. Often it's a common thing where we'll just be given partial information, but enough to put together the table for ourselves. So although we've got the full counts here, I'm just going to pretend that this is an exam and somebody has given me a question like this, and they've just said, out of the 94 people who tested positive, 92 were confirmed to have the virus, and of the 4,559 who tested negative, 4,523 were confirmed to not be infected. And so from that we are expected to be able to put together the table. So we sort of have to identify words like "of the" usually are referring to something in the margin. So of the 94 who tested positive, I can probably put that in, 94 were positive, therefore 92 confirmed to have the virus. That leaves 2 who tested, who were not confirmed to have the virus, where it was a false positive. And similarly, if we've got our 4,559 who tested negative and 4,523 were confirmed to not be infected, then whatever the difference is here, 36, that should give us our totals over here. So and just drag that down. Alright, and we should be able to check that that matches up with, in this case we can flick back to our table, 128, 4525, 4525, 128. Perfect. So yes, so sometimes we're going to have to put together our table first so that we've got the full counts to work with, because we will need our marginal totals, our overall totals, to calculate most of the probabilities that we're after. Alright, once we have our full table, we then get questions that will have a variety of wordings, and the three that we're kind of looking for are, if it's a marginal question, it will be a question that purely asks about one thing on its own. So what is the probability of an overall no? Or what is the probability of an overall yes? Or what is the probability that a person tested positive? Only mentioning one of the two variables of interest in our data set, and so we can identify then that we're talking about a marginal probability. If we have wording that says and or both, so what is the probability that a person both tested positive and was confirmed to be positive, then we know we're talking about a joint probability. Keyword being and. And finally then there's conditional probability, where we will get wordings like given or if. So one of the things is already assumed to be true or already has been observed, and the other one is asking what is the probability of the other one given that has happened. So what is the probability of a person actually having the virus given that they initially tested positive? Or what is the probability of being truly COVID-19 negative given the first test result came back negative? So keywords like given or if are what we look for in those situations. So here's just a little graphic to help us see how we would calculate those things. So if we are asking about just one thing on its own, well, we know that's got to be a marginal one. And marginal ones, it's pretty straightforward. We just look for the margin that corresponds to that thing. So if we want to know what is the marginal probability of actually having COVID-19, in our case being a yes, then we go out to the margin for yes and divide by the total, which we do for most things. So we would end up with 128 over 4653 will give us our marginal probability of actually having COVID-19, which comes out at about 3%. So not many people actually had the virus at the time this data was collected. If we have wording that says something like testing for two things at once, what is the probability of testing positive and actually having the virus? We know we're talking about a joint probability. And for that, we're looking up two things in our table. First of all, positive and yes at the same time, and we just look for where they intersect. We get our 92, and once again, we divide by the total. So our joint probability we can calculate with that cell divided by the overall total gives us an overall probability of about 2%. So you are even less likely to have both had the virus and initially tested positive. And finally, if it's a conditional probability that we're after, we need to just be very careful about which thing is the one that is given. So conditional, one of the things is already given to be true, and we want to know the probability of the other. It's always the thing after the bar, so the thing that is given is the one on the right of our little given thing here. And I find the best way to try to calculate conditional probabilities is, once you know what is given, just cover up all the rest of the table. So if we know it is given, if the question is, what is the probability of actually having the virus given that you initially tested positive to COVID-19, well, we can cover up all the rest of the table apart from the thing that is given, and then it becomes very easy to see what we should use. What's the probability of yes? Well, it's going to be 92 over the total, which is now 94. So 92 out of 94 is going to be 0.9787. So about 98% chance that you really did have the virus, given that you initially tested positive. Great. Let's try that out in the tutorial and see if we've got some others. Oh, let me just quickly see in the assignment. What sort of wording do they use here? So what is the probability that a randomly selected component? Well, that's presumably talking about something overall. It's not just one thing on its own. It's asking about faulty and overseas. It's asking about two things at once. So hopefully we'll be able to see what type of probability that is. If a randomly selected component is found to be faulty, what's the probability it was made in New Zealand? Okay, well that sort of sounds like something is being given in advance and then calculate another. And if a randomly selected component is from a New Zealand factory, what's the probability it's faulty? Okay, once again, something possibly being given. And alright, and then those others will probably be on independence. Alright. Let's try doing a couple more using the questions that we've got in the workshop. So we've got the table up here that we can look at, but when we're working in R, we want to turn those totals into numbers that we can call up quickly. And so in this case, they've been designated as YN is going to be yes, you were confirmed to have the virus, N for tested negative. So this is our YN is the confirmed yes and the negatives. YP, yes, you had the virus and initially tested positive. NN for no, you didn't have the virus and you tested negative. And NP is the no, you didn't have the virus, but you did test positive, the false positive group. Then our marginals, just add those together, and a total, add the marginals together. Great. All right. So let's see. Here, could be asking us what is the probability for of an overall yes. Well, we've already done that one in the other thing. Let's do what is the marginal probability of a no. We could take 1 minus the probability of yes, but let's just do it as though we were. Overall probability of a no, we go out to the margin and divide by the total. which is going to be, in our case, the no's divided by the total. So let's just make sure I run that in here. No divided by total gives us 0.972. Cool, that looks right. Most people did not actually have the virus, and we should also just try what they did before, which is 1 minus yes. So PS is yes over total. Cool. And 1 minus PS is going to give us the same answer, hopefully. Great. Perfect. Everything's working well in our tables. These things should add up to the total, so great. What about a joint probability? All right. Well, they've got what is the probability of yes and positive here, but I'm going to try and invert that and do what is the probability of no and positive. So another way this question could be worded would be, what is the probability that a randomly selected person both tested positive and did have the virus? So I'm going to do it. What is the probability that the randomly selected person did not have the virus and tested negative? So if we're asking about two things at once, this is a joint probability. So we'll be looking up both of the things we're interested in, find the cell in the table, and divide by the grand total. So we want no and negative is going to be NN divided by total. And we get 97% chance. Probability of both testing no and have initially testing negative is 97%. Great. What about the next ones? Conditional probabilities. All right. Conditional probability puts a condition on what can happen. Something is given. So in this case, let's try. They've got what is the probability of a yes given that you tested positive? Well, I want to try a different one. I'm going to ask, what is the probability of not having the virus given that you initially tested positive? That is, say I've gone in and taken a test and I've tested positive, what's the probability that was a false positive, that I'm actually okay? So I want the probability of no given positive. Alright, from our thing, if this is a given question, then this is going to be a conditional probability. So we want to go look up what is the thing that is given. So assuming that positive is the thing that is given, we can cover up the rest of the table, and we're just interested in, out of a total of 94, what is the probability of a no? Well, we just get the entry for that cell, 2 over 94, or in our R thing, it's going to be no and positive divided by the total for positive. I could, of course, just be typing the numbers in directly here, and it would work just as well. Only a 2% chance of a false positive. That is, if we had initially tested positive for the virus, there is just a 2% chance that we are actually okay, and that this is a clinical mistake from the test. Great. Right, the next little section that we're being asked about is questions on independence. So I won't do this exact question, but this one's asking us, if you could assume that these two things were independent, what would be the probability of one or the other? So let's jump back to our example. Now, one of the things we know about independence is if we can assume that these two things are independent, then the numbers that you see in the table should really just be a function of the totals that you have down on the ends of the columns. And this corresponds very closely to our chi-squared test, where we calculate the expected number that you would have in a given cell, and then compare it to the observed one to construct our chi-square test statistic. So I could call this our observed counts, and I could also compare it to our expected counts under the null hypothesis that they really are independent. So if I just delete all the actual numbers, no, actually I need that. Let's just overwrite this to be great. So if these things really are independent, the number that you get in this cell should just be the column total times the row total divided by the grand total. That is how chi-square test statistics calculate their expected value. So I'll do that. Times this divided by this gives us 125. And so you can kind of see the way this is working is the vast majority of people initially tested negative, and only a small portion actually had the virus. So this should be a relatively small number out of the total here and out of the total here. By comparison, this one should be column total times row total divided by grand total. Only a very small number of the people tested positive initially, and it's a very small number that were confirmed to have it, so we expect a very small number of people to test positive and to actually have the virus, only 2.58. Here, column total times row total divided by grand total. Oops, did I get that wrong? What have I done there? Yes, sorry, that should not be I3. And of course I could be doing this in R, but I just thought this is a visual guide to how it's being done. Might make it a little bit easier for you. Alright, so immediately we can sort of compare what we observed with what we expected. But I think the question initially being phrased in the exam thing was, in the assignment was, what probability of things would you expect if they really were independent? So to phrase that for our example, if the probability of actually having the virus was independent of your test result, what number of people you would expect to see who were tested positive and confirmed to have the virus? Well, the expected number is 2.58, so 3. We would expect to see 3 people approximately who both had the virus and tested positive if these two things really were independent. That would be a bad sign for the test if its probability of being a positive result was independent of whether you had the virus or not. It would show the test does not work at all, or that it's a totally fake test. We can immediately look at the actual table and see, well, they are probably not independent. The probability, the number of people who actually had the virus and tested positive was much, much higher than we expected. And the number of false positives, or people who didn't have the virus but tested positives, was much lower, as it should be. And the same over with the initially testing negative people. We expected to see about 4,430 who initially tested negative and were no's, but more of those people were actual no's than we expected. And of the people who tested negative initially, we would expect, if they were independent, 125 to actually have the virus. Only 36 of the people who tested negative then turned out to have the virus. Great. So from that, we can directly answer. It's the way the question was phrased down here is, what is the probability that a randomly selected component will be produced overseas? So in that case, well, we just need to be careful to convert our totals here into a probability. If this is a joint probability, like assuming these two things are independent, what is the probability of a person testing negative and having the virus at the same time? Well, a joint probability, we take the cell divided by the grand total. So the probability of yes and negative, assuming independence, is 0.02 or 0.03 if you're rounding to the nearest 2 decimal places. Great. Alright, the next little section we would want to do is a test of independence. Now, in the assignment, the way this question's worded down here, justify why you believe the fault rate of parts is or is not independent of where they were manufactured. I think that wording is deliberately not formal, not saying perform a hypothesis test. So I believe that probably just talking about what we saw on the tables, comparing the expected counts to the observed counts, would probably be sufficient to answer that question, to at least justify beyond reasonable doubt that these things are or are not independent. So that would probably be absolutely fine to just talk about those totals and how they differed and how much they differed by. But of course, we do statistics here. We may as well do a hypothesis test to try and prove it beyond reasonable doubt. And the way we've been shown to do that is the chi-square test, which is formal statistical hypothesis test of whether or not this two-way table is independent. Unfortunately, our data are not like in these ones. They were already prepared for us to be in a table, and so but ours are not for this example. So I've just tracked down some code here to put the table into R. So basically, I'm just creating a new object called testing, and I just want to put in my counts manually, just being sure to make sure I know what order they're going in. So this is filling up the table by rows. So first row is going to be, as we saw, the yeses. So it's going to go 36, 92, then 4, 5, 2, 3, then 2. And 36, 92, 4, 5, 2, 3, 2. And then once I've created that testing object as a matrix, I can then label the columns negative and positive, as they are in our thing, negative, positive, and then the rows yes and no. And then if I say as table, it should give us an object called testing, which is our table of counts that we've been using. So that matches up here. Good. Yep. Positive and no is 2. Yep. Good. Okay. All looks right there. Then we should just be able to use what we've got in our test of chi-square test of independence. We should just be able to pipe that testing object into the chi-square test. And now it's giving us a warning, probably because some of our expected counts are very low, and the chi-square test is not perfectly accurate if you have very low counts. In particular, I think we had one or two cells where the expected count was less than 5. I think that warning is issued for that, but that's still probably just fine because the chi-square statistic is so highly significant. So we can see chi-square 3208, 1 degree of freedom, and the p-value is the smallest one that R will calculate for us, approximately 0. P is 0.00000, 15 zeros, then a 2. Which is just R giving the smallest value it can. So there we can do a formal hypothesis test of our thing, and we conclude we reject the null hypothesis that the two things are independent. We have highly significant evidence that that in this case the probability of testing positive or negative does depend on whether you have the virus or not. Or you could phrase that the other way around. We have statistically significant evidence that the probability of actually having the virus or not strongly depends on whether you tested positive or negative initially. Great. Well, if you like this tutorial video, I'll do some more for the other questions as well.